So we're not here yet. Let's see here. Where did we finish up? That is. Did we finish this one here? No. Yes, sir. Okay.
Yeah. Yes, we are. Yes, we are awesome. Be real with me.
All right, guys. So what we started Friday was applying these horizontal and vertical translation, moving the graph up or down, or left and right. And where we finished off Friday was this here: f of x equals the absolute value of x minus 3. Now we're going to translate it 4 units to the right. Now they didn't give us a name for the function, but we can call it g of x equals. So our horizontal translation, write this one, is f of x minus h is the general form. So for here we have f of x minus h as the general form for our horizontal, our left and right. Now our value for h of this here is going to be what? 4. Now since it's moving to the right, the value of h, this 4, is going to be positive. If it was moving to the left, the value of h would be negative 4. Now the next thing we can do is to plug that value of h into the general form, giving us f of x minus 4. Now we don't have f of x anymore because this x has been replaced with x minus 4, which means every x in the function has to be replaced with x minus 4. So when we do this, we'll have the absolute value bar still. But instead of x, we have x minus 4. Absolute value bar minus 3. So everything else stays the same. We're just taking that x and replacing it with what's inside our parentheses for f of x. Now inside the absolute value bars, is there anything in front of that set of parentheses? No. So we can drop the parentheses. So we'd have the absolute value of x minus 4 minus 3. Now we also don't have to rewrite this whole g of x equals f of x minus 4. It is just g of x because this is our new function. I wrote it that way just so that we could see that g of x is equal to our f of x minus 4, which is equal to the absolute value of our x minus 4 minus 3. Now, are there any like terms? Yeah, no. Negative 4 and 3 technically are like terms because they are both constant terms, but because of the absolute value, they're stuck apart. We can't actually combine them. We can't combine across that absolute value. So that there is the final answer. That's all we have to do. Questions on our left, right, up, down? Yeah. All right. What we're going to look at next is reflections. Oh, wrong button. There we go. Reflections. Now, again, we do have a lot more here, but the key thing is the general forms. So our reflection across the x-axis, a reflection in the x-axis is going to be negative f of x. Now, I do have it already on the whiteboard, so whenever we're applying a reflection across the x-axis, we're going to be using the negative f of x. Now, if we're going to be reflecting it in the y-axis, we're going to do f of negative x. So across the y is f of negative x, across the x is negative f of x. And again, we're going to be using this general form depending on what we're applying. Let's actually see it in a problem. This one here. Now, hopefully the slides look a little bit nicer than they were a minute ago. I did go back actually at the end of last hour and change it because it was bugging me all day. Because if it looks a little blurry out there, it really looks blurry up here. Now, what we're wanting to do here is write a function whose graph is a reflection in the x-axis of the graph of f. So our new function's name is g of x. Now, the general form for a reflection in the x-axis is negative f of x. Negative f of x. Now we still have f of x. We just have a negative in front of it, yes? So all we need to do is replace f of x with its function. Well, f of x is the absolute value of x plus 3 plus 1. Now, in some of the problems we've done up to this point, we really didn't need the parentheses because we ended up dropping them and nothing changed. Here we do need the parentheses because that negative 1, we just write it as a negative, is going to have to be distributed through the whole function to every term. Now, the first term we're going to distribute this to is the absolute value. Now, we're not multiplying the x plus 3 by the negative 1. We're multiplying the number in front of it. Now, there's not a number specifically written there, but what is it understood to be? 1. Because if the number's not written, it's understood to be 1. So we're multiplying that 1 by a negative, which would make it negative 1, or we can just say negative absolute value of x. So the absolute value went from positive to negative. But we also have to multiply this negative by our plus 1, which is going to make it minus 1. Questions on this here? We ready for the next step? Box it. That's it. That's it, because there's no way to combine like terms. We can't combine the 3 and negative 1 because of the absolute values. And if we did move the negative inside the absolute value, the properties of absolute values would just get rid of it. Absolute value x. Yeah, so we have negative, the absolute value bar x plus 3, absolute value bar minus 1. Questions on this here? Good with this so far? You ready for a reflection in the y-axis? Well, it's right here. Now, we've talked about reflection in the y-axis a little bit last week. but we didn't actually see any come up. Here we're going to apply a reflection in the y-axis. So we want to write a function h whose graph is a reflection in the y-axis of the graph of f. So h of x equals, well, the general form for a reflection in the y-axis is f of negative x. So what we're going to do with this here is similar to what we did with the left-right, because we have f of negative x, not f of x. So every x in f of x is going to be replaced with negative x. And our absolute value of x plus 3. So here we're going to replace every x, replace this x with negative x, which means this x also has to be replaced with negative x. So we have parentheses, or our absolute value, not parentheses, in parentheses negative x plus 3 plus 1. I'm not removing it, I'm just trying to make it look a little nicer. So we replace every x in f of x with negative x. Questions on this so far? Is there something in front of the parentheses with our negative x? No. So do we need them? No. No like term, so that is there. That's it. It's done. So how do we feel with most of these transformations? They're pretty nice as long as we're sticking to these formulas, because we apply the formula to it, these general forms, everything kind of falls in line, yes? Now, we won't get there today, but we can apply other transformations. We can do more than one. We can do more than one transformation to these functions. And really, it's nothing more difficult or harder than what we've already done. Because we would do like this here. I applied a reflection in the y-axis. Then we could say we translated it up 4. So I would take what we just finished with, do our vertical translation, the f of x plus k, and we would apply it to this here. So essentially it's doing the same thing, but not applying it to the original, but the one we did here. But we will be doing that tomorrow. Let's look at, so how do we feel about reflections? Pretty good? At least see 2 more, and then we'll move on. Let's look at this one here. F of x equals the absolute value of x minus 5 minus 4. We want to write a function h whose graph is a reflection in the x-axis of the graph of f. So, h of x equals negative f of x. So the general form for across the x-axis is negative f of x. So we're talking about a reflecting across or reflection in the x-axis, it's negative f of x. When it's in the y-axis, it's f of negative x. Well, for this here, our next step is going to be replacing f of x with its function. So we'll have parentheses, x minus 5 minus 4. And the last thing we need to do is distribute the negative. Now we are going to multiply our absolute value of x minus 5 by that negative, which gives us negative absolute value of x minus 5. It just goes in front. Questions on this here? Now we also need to multiply the negative by the negative 4. And a negative times a negative is a positive. So our final answer is negative absolute value of x minus 5 plus 4. And that's it. Questions on this here? Do we feel good with these here? Let's look at one more of these reflections and then we'll move on to stretch and shrink. Question? Write a function g whose graph is a reflection in the y-axis of the graph of f. So if we're talking about a reflection in the y-axis, our general form is f of negative x. In the x-axis, it's negative f of x. In the y-axis, it's f of negative x. Y-axis is f of negative x. X-axis is negative f of x. Questions? So now we have f of negative x. Since we replaced this x with negative x, it means we have to replace this x with negative x. So we'll still have our absolute value bar. But our x in the equation is now, let's sort of mix this because I want that to be light green. Negative x minus 5 minus 4. Questions on this here? Is there anything in front of our parentheses? No. So it's just going to be negative x minus 5 minus 4. And that is it. Any questions on any of these here? Do we need to see another example with reflection across x or y? Able to see? Yes? No?
Don't lie, Dave.
Okay. You borrowing glasses? Okay. So if we feel good with reflection, we will move on to the last type of transformation. Horizontal stretch and shrink. Now, and vertical stretch and shrink. Out of these two, we're going to look at vertical stretch and shrink first. Vertical stretch and shrink, the general form is a times f of x. Doesn't matter if it's stretch, doesn't matter if it's a shrink. We still use the same form, where a is the amount that we're stretching or shrinking the function vertically by. So if it's a vertical shrink of 1/3, we're still using a times f of x. If it's a vertical stretch of 7, we're still using a times f of x. Doesn't matter if it's a stretch or shrink vertically, we still use the same general form. Horizontal stretch or shrink. Our general form for this here is f of a times x. But we have to flip the value. Whenever it's a horizontal stretch or shrink, the amount that they give you, you need to flip it. You need to flip the value before you plug it in for a, before we attach it to a. So if they told us that it's a horizontal stretch of 4, the a value is actually 1/4. We have to flip it. If they tell us it's a horizontal stretch or shrink of 2/7, the A value that we would plug in is 7/2. We have to flip that value of A for horizontal stretch or shrink. Horizontal stretch or shrink, you've got to flip that value of A for us to get the right value. And that's really what they're saying by this 1/A. 1/A, we're flipping it. We're flipping that value. Now, luckily, the first one we're going to look at is not horizontal. We're going to look at vertical first. They gave us this function here. F of x is equal to the absolute value of x minus 3 minus 5. We want to write a function h of x, whose graph is a vertical stretch of the graph of f by a factor of 2. Now, since we're talking about vertical, we're doing a times f of x. A times f of x, where a is the amount we're stretching or shrinking the graph by vertically. And here our a value is what? 2. So in the general form, since a is 2, we're going to replace a with 2. So we get 2 times f of x. Questions on this here? Okay. Now we still have the function f of x, yes? So just like with vertical, or reflection across the x-axis, or any of these here, we're just going to replace f of x with its function. So we're going to have 2 parentheses absolute value of x minus 3 minus 5. Now just like with our reflection across the x-axis where we distributed the negative through, here we're not going to distribute a negative, we're going to distribute the 2. And just like with the negative, we're not going to multiply through the absolute value of x minus 3. We're just going to have 2 times the absolute value of x minus 3. We're just going to leave it in front. Now 2 times negative 5 is negative 10. That's it. Questions on this here before we look at the next one? Or do we feel good with this here? This next one here, we want to write a function g of x, whose graph is a horizontal shrink by a factor of 1/3. So since it's talking about a horizontal shrink, we're looking at g of x equals f of a times x. Horizontal stretch and shrink, we have to be careful because the factor of a is not going to be the number they give us. It's going to be flipped. Anytime we have horizontal stretch or shrink, we have to flip the factor that it tells us. Well, what happens when I flip 1/3? We get 3. 3 over 1 or 3. So our value of a is 3. Okay? Because it seems like it should stay 1/3 because that's how they've been working. We take that value, plug it in with its sign. But here we have to flip it. So what it's telling us, and when we plug it in here, that we have f of 3x. When we plug that value in, we get f of 3x. questions on this so far, on how we did this? All right. Now we don't have f of x anymore, we have f of 3x, which means every x in f of x is going to have to be changed to 3x. So we'd still have the absolute value bar, but instead of x we have 3x minus 3 minus 5. Questions on this here? So, what we've done to the function with this horizontal shrink. So vertical stretch, it increased faster along the y-axis. It went up quicker. It was narrower. Vertical shrink, it opened it up. It increased slower on the y-axis, yes? So here, if it's a vertical shrink, it should be increasing slower along the x. That means it should be narrower, yes? So, let's look at this here. Okay. None of these are what we wanted. So we do want absolute values of 3x. So it's x minus 3 plus 1, is it? Minus 5. So this here is our original graph. Now, math, numbers, 3x minus 3 minus 5 is the one that we came up with. Now, it feels like we should have, now, I did it with 1/3 because that's the one that it gave us originally, yes? Because that's the value it gave us. Let's see what it would look like if we'd have used 1/3 instead of 3. Did that graph get smaller, or did it increase faster along the x-axis? When it increased faster, it got wider, yes? So that's part of the reason we can't just leave it as 1/3. So now if we look at the one in red, is it increasing slower? Well, yeah, because it wanted to be a vertical shrink. We wanted to shrink the x-axis down. Now it didn't move the bottom part of the V, it's just one of the parts of it. But it's increasing slower along the x. Where this one here is increasing faster along the x. It's increasing slower along the y, but faster along the x. That's why it's called a vertical or horizontal shrink. It is a little bit confusing, but the key thing is, whenever we do horizontal stretch or shrink, we've got to flip that value of A, flip that value they give us before we plug it in. Does that make sense? Do y'all want to see another horizontal? Yeah. Because horizontal is one of the more confusing of this group, out of all of them. Well, we want to write a graph G. Write a function G whose graph is a horizontal stretch of the graph of f by a factor of 5, yes? Well, as we just saw, the graph that was in black was indeed a stretch, yes? But the number that was in the function was not a whole number. It was what, a fraction, yes? Yes. So we have to flip it. So our flip of 5 would be 1 over 5. Since 5 doesn't have a denominator, it's understood to be 1. So we flip it as 1 over 5. So our value for A for this is 1/5. So we have f of, come on. Okay. One-fifth x. So it gave us 5, but before we can plug it in, we have to flip it. So our value of A that we're actually using is 1/5. Now the only time we do have to flip this is when we're talking about a horizontal structure shrink. Vertical structure shrink, it stays exactly how it is. Now our next step is to plug that 1/5 x into every x in f of x, which gives us g of x is equal to the absolute value of parentheses 1/5 x minus 1 plus 2. Is there anything in front of those parentheses besides the absolute value bar? No. So we can drop them. And that's it. So the only key to horizontal is making sure to flip that value of A that they give us, that value of the structure shrink. Because for us here, applying that transformation, it's nice to know if it's a structure shrink. But once they give us that value, we need to flip it. And that is it. Questions on this here? We feel good with this here. Well, the next one, the last one we're looking at today is this one here. Write a function h whose graph is a vertical shrink of the graph of f by a factor of 0.25. Well, what's our value of A? Well, it is 0.25. Because the function or the problem told us what our vertical shrink is going to be. So that's our value of A. And the first thing we can do is plug that value in for A, telling us that our g of x is equal to 0.25 times f of x. Now we can plug in our f of x. So we replace f of x with our parentheses, absolute value of x, minus 1 plus 2. And last thing we need to do is what? Distribute the 0.25. Now we multiply the 0.25 by our absolute value of x minus 1. We just get 0.25 times the absolute value of x minus 1. But we also need to multiply this 0.25 by 2. Since they're both positive, it's going to say plus. But now we need to do 2 times 0.25, which is 0.5. You got 2 quarters. Makes 50 cents. questions on any of this here? I'll stop here for the day. We'll start with some more vertical stretch strength, horizontal stretch strength tomorrow.